Hey everyone! Have you ever looked at your face in a shiny steel spoon and noticed that sometimes your reflection looks tiny and upside down, while other times it's big and upright? Well, that's not magic, it's physics in action. Those spoon reflections happen because the spoon acts like a spherical mirror, a curved surface that reflects light differently depending on which side you're looking at. When the inner surface reflects, it's called a concave mirror, it converges light. When the outer surface reflects, it's a convex mirror, it diverges light. Now, let's get familiar with the parts of these mirrors. The pole, P, is the geometric center of the mirror surface, the center of curvature, C, is the center of the imaginary sphere the mirror belongs to, and the radius of curvature, R, is its radius. The principal axis is that straight line connecting P and C, the mirror's central guide. And there's one more key player, the principal focus, F, the point where rays parallel to the axis converge or appear to diverge after reflection. So next time you eat with a spoon, just remember, you're holding a physics lab in your hand. Alright, now that we know our mirror's anatomy, let's see how it behaves. Every curved mirror, no matter how fancy, still obeys the same two laws of reflection. First, the incident ray, reflected ray, and the normal at the point of incidence all lie in the same plane. Second, the angle of incidence equals the angle of reflection, written as I equals R. In a spherical mirror, these laws hold for every tiny point on the surface. That's why we can still predict how light behaves. For example, any ray parallel to the principal axis will pass through or appear to come from the focus, F, after reflection. Rays passing through the center of curvature, C, reflect back on themselves, while rays hitting the pole, P, reflect symmetrically, making equal angles on both sides of the normal. As you can see in the diagram, these rules create the foundation for how images form, whether they're upright, inverted, or magnified. Now, let's focus on the star of the show, the concave mirror. These mirrors can do everything from focusing sunlight to magnifying your face in a makeup mirror. The nature of the image changes depending on where you place the object. If the object is beyond C, the image forms between F and C, it's real, inverted, and smaller. If the object is at C, the image forms at C again, same size, real, and inverted. Move the object between C and F, and the image shifts beyond C, becoming magnified and inverted. But if the object is between F and P, something magical happens, the rays diverge, and your brain traces them back behind the mirror. The image becomes virtual, erect, and magnified. That's why a shaving or makeup mirror, which is concave, makes your face look larger when you're close. Now let's meet the convex mirror, the mirror of safety. If you've ever looked at your car's side mirror, you've read that line, objects in the mirror are closer than they appear. That's a convex mirror at work. No matter where you place an object, a convex mirror always forms a virtual, erect, and diminished image behind the mirror. The reflected rays spread out, but when extended backward, they appear to meet at a virtual focus. The behavior of these mirrors is described by the mirror formula 1 by F equals 1 by V plus 1 by U, where F is focal length, V is image distance, and U is object distance. For both mirror types, the relation are equals to F holes connecting the radius of curvature and focal length. Convex mirrors are used in vehicles and stores because they provide a wider field of view, safety through smart optics. Let's do a quick calculation together. Suppose an object is placed 30 centimeters in front of a concave mirror with a focal length of 15 centimeters. We'll find the image distance and magnification. Step 1. Use the mirror formula 1 over F equals 1 over V plus 1 over U. Now, substitute the values 1 over 15 equals 1 over v plus 1 over negative 30. Simplify it, 1 over v equals 1 over 15 plus 1 over 30, which equals 1 over 10. So, v equals 10 centimeters. The image forms in front of the mirror, real and inverted. Now, for the magnification, we use the formula m equals negative v over u. Substitute the values m equals negative 10 divided by negative 30, which equals 1/3. That means the image is 1/3 the size of the object, smaller but perfectly proportioned. Always remember to apply the sign conventions, negative for distances measured against incident light and positive otherwise. One wrong sign can flip your entire answer. Let's wrap it all up. Spherical mirrors are curved reflectors, concave mirrors converge light, while convex mirrors diverge it. Concave mirrors can form both real and virtual images depending on where the object is placed. Convex mirrors, however, always form virtual, erect, and diminished images. These mirrors aren't just textbook concepts, they're everywhere. From car headlights and dentist mirrors to security domes and telescopes, they guide, reflect, and expand our view of the world. So, next time you glance at your reflection, remember, behind that simple image lies the elegant geometry of spherical mirrors and the beauty of physics itself. See you in the next session, where we'll explore how light bends in refraction of light.